What's the question?
1C, sir.
1 part C, that's you can calculate the solubility in grams per DMQ of barium sulfate is so the solubility product is known, right? So what is the solubility product? Like barium sulfate is going to dissolve in a saturated solution. It's going to be in equilibrium with its aqueous ions, which are these two ions. You got barium aqueous and SO4 minus 2 aqueous. So your KSP expression is going to be the product concentration and divided by the reactant concentration. The reactant is a solid, so that's 1. So now they're asking what is the solubility. Now you know the KSP value already. That's 1.08 times 10 power minus 10, right? So that is already known, whole square d minus 6, right? So they want to figure out what is the solubility. So if X mole per dmq of barium sulfate dissolves, right? So it's going to produce X barium ions and X sulfate ions. Is that clear?
Yes, sir.
So the concentration of barium ions is X and the concentration of sulfate ions is also X. So that's 1.08 times 10 power minus 10. So it becomes, so what is your X? It's X squared is equal to, so X will be 1.08 times 10 power minus 10. And you're going to underroot the whole thing, right? Is this clear?
Yes, sir.
So you're going to underroot the whole thing. What do you get if you underroot this?
1.04 times 10 to the power negative 5.
So that's what X is. That's the amount that is dissolving, right? That's the amount of barium sulfate, right? That is mixing in the solution. Is this clear?
Yes, sir.
But now he wants it in gram per. Now that's kind of weird. Like he wants it in gram per 100 cm cube, right? What I'm going to do is I'm going to convert this into grams per dm cube. How do I convert moles into grams? I'll multiply it by MR, by the molar mass, right?
Yes,
So the
sir.
molar mass of this thing is, I don't know what barium is, but I think it's 137. I guess it's 137. So mass will be 1.04 into 10 to the power minus 5 moles times MR. So can you figure out what the MR is? It's 137.3. SO4 is 96.1 actually.
Sir, they multiplied it by 233.4 over 10.
Yeah, I'll come to 10. First tell me what the mass is.
Okay, sir.
And what do we get for this?
Barium is actually 137.3 plus sulfate, so that's sulfate, that's 32.1 plus 4 times oxygen, 16. Yeah, that's 233.4.
Hey, okay, that's 233.4 and that's going to be multiplied by moles, that's 1.04 times 10 power minus 5, right? So how many grams do you get per dm cube?
2.427 times 10 to the power negative 3, 2.2427, so 2.43 times 10 to the power negative 3.
2.43 times 10 to the power negative 3, right?
Yes, sir.
Grams per dm cube. Dm cube is like 1000 cm cube, right?
Yes, sir.
So he's asking per 100 cm cube, right? So if it's so you can just use ratios, like you've got 2.34 grams of 1000 cm cube, so in 100 cm cube you're going to have how much? You're going to have X cross multiply, it's going to be divided by 10 then. Is this clear?
Yes, sir.
You've done this paper, right?
Just a bit of it. I was also doing, sir, the D part one for the lattice energy.
With this one?
Yes, sir.
It's saying,
So, my question was, to find the lattice energy, it's supposed to be lattice equals to, basically everything relating that element minus formation of the compound. Is that the formula, sir?
you have to draw the cycle. You have to draw the whole cycle. So the
Okay, sir.
thing over here is that the equation for the formation of gaseous sulfate ion is this. They've given you this. It may be helpful to draw, use data. What calculate standard enthalpy change of formation of SO4 minus 2, right? So he's asking you to calculate this thing. And they gave a lot of stuff about barium sulfate, right? So what we're going to do is we're actually going to do the barium sulfate lattice energy, right? So what you do is you start off with enthalpy of formation. You can remember this hair cycle. You always start off with enthalpy of formation. That makes things easy. You got barium solid, plus you got sulfur, which is solid, plus you've got oxygen, which is gas, and it's forming, and this thing is forming barium sulfate, right? Which is a solid. And that enthalpy of formation is this one. It's minus 1473. Is this clear? See, is this clear?
Yes, sir.
I said, then what happens is you start doing everything stepwise. Then what you do is you start doing everything stepwise. Like, what's the first thing? Atomization of barium. So what I'm going to do is I'm going to atomize barium. So what I'm going to do is the barium is going to turn into gas. The sulfur remains the same. The two oxygen gas molecules, they also remain the same. So the atomization is 180. What else is given? The first and second ionization energy of barium is also given. So what I'm going to do is I'm going to ionize barium. I'm going to turn it into an ion, and it's going to lose 2 electrons. And sulfur is a solid, so I'm not touching it. And 2 oxygens, which are gases, I'm not touching that. So what is the
Sir,
first? Haji.
sir, why aren't we atomizing sulfur at the same time as barium?
I mean, we should do that, but I'll tell you why we're not doing that. Okay. I mean, according to the body cycle, we should. I mean, you can do it in 2 steps, or you can do it in all together as well, right? Clear, Amina?
Yes, sir.
But there's a reason why I'm not doing it in this case, because first thing, they didn't give us the atomization of sulfur. They actually did give us the atomization of sulfur, by the way.
It did, sir.
So I'm going to do that next. So anyways, barium is ionizing, so that's 503 plus 965, right? So now, here's the thing. Okay, I'm not actually. Okay, what is the Born-Haber cycle, by the way? It's you have enthalpy formation, you've got elements, right? I mean, this is the general sketch of a Born-Haber cycle. You have elements in the standard state. They're forming an ionic lattice, right? What happens is you atomize the elements. Then what do? You ionize them, and when they become ions, you form the lattice. That's your lattice energy, right? And this thing over here is your delta HF. Now that is the sketch of every Born-Haber cycle. Elements turning to ionic lattice. You atomize the elements, you ionize them, and then when the ions get together, you form the ionic lattice, right? Now, what I've done is I've done the atomization of barium, and I've done the ionization of barium as well. I haven't touched sulfur, and I haven't touched oxygen as well. And there's a reason for that. The reason is, Okay, they want me to calculate this thing. Sulfur solid plus 2 oxygen gas plus 2 electrons turning into SO4 minus 2. Okay, so somewhere in the cycle, I need to incorporate this thing because this is the unknown enthalpy change which I'm trying to figure out. Okay, sulfur solid with 2 oxygen gas, 2 electrons turns into SO4 minus 2. I have exactly the same thing. I've got sulfur solid, I've got 2 electrons, and I've got 2 oxygen molecules. So I'm going to the unknown equation. I'm going to put it in this at this part. Okay, the barium will not change. Nothing happens to barium. So barium remains as plus 2 gas. What happens is, okay, the sulfur solid with 2 oxygen gas plus 2 electrons turns into SO4 minus 2 gas. So I'm going to do all of that in one step, SO4 minus 2 gas. This is the unknown enthalpy change that I'm trying to actually solve for. Is this idea clear?
Yes, sir.
Yes, sir.
Okay, so this is the one that I'm trying to actually figure out. Okay, and in this step, the barium did not do anything. And then what's going to happen is the ions will get together and they would form the ionic lattice. That's your lattice energy. So the lattice energy, I think, is given as well. That's minus 2,4. That's minus 2,469. Okay, that is given. So the thing is, I could have drawn a normal bond neighbor cycle, but I decided not to actually. I decided to jump because I mean this entire path which had to be incorporated into the cycle. Okay, I mean I could have drawn the whole bond neighbor cycle as well. Actually, I still couldn't. I would have gotten stuck if I had actually even tried to draw the whole bond neighbor cycle. Because over here I've got I would have gotten stuck with the bond neighbor cycle part. I mean, this thing had to be incorporated. So, anyways, one path is equal to the other path. So that's path number one. Call that P1, and that is path number two. So that means minus 1473 is equal to the rest of these. It's equal to 180 plus 503 plus 965. That's plus it's X, and then it's minus 2469. Okay, so what do we get for X? Can you try and figure out? It's plus 965 plus 14 minus 2469.
652, sir.
How much?
652.
6.2?
652, sir.
652, right?
Yes, sir.
And I hope that's the answer, 652 kilojoules per mole. We can just quickly check this one. And be very careful with these bond neighbor cycle questions. Just a second. So this one is they're saying it's minus 652.
Sir, I got minus 652 as well because I think you forgot to make 2469 positive when you send it to the other side.
Which ion positive?
The I think the lattice energy negative 2469. When you send that to the other side, it will become positive. So that's why I also got minus 652.
What I did wrong was that what I did wrong was that this is minus X actually. I actually sent the X on the other side. So this was actually minus X. So plus 652 was fine, but plus 652 was actually equal to minus X. So X would come out to be minus 652. So everything was right. We made a silly mistake with the negative sign over here. I forgot to add the negative sign. Okay. Zina, is this clear?
Yes, sir.
So now the next, should we try and do the same paper?
Yes, sir.
As I suggest how
Yes,
the
sir.
as I suggest how the lattice energy of differs from the lattice energy of CS2SO4. I have no idea. Did they give us the lattice energy? I don't think so. They did. So anyway, so how would the lattice energy differ from? You got barium. Who's got the stronger lattice? One hint is that this is -2, cesium is +1, and barium is +2 and -2. So if you've got greater charge, right? So will you have a stronger lattice or not?
Yes, sir.
So greater charge, which means greater charge density as well. And it's going to be a smaller ion as well. Now, how do I know that it's a smaller ion? I think in the periodic table, cesium and barium are right next to each other. This is group 1 and this is group 2. Uh, this I
Radius?
are they in they're in the same period, right?
Yes, sir.
So what happens is that cesium, when you go across the period, the size of the ion decreases. Remember that. Why? Because you got more protons. I don't know how many protons barium has. I think it's got 56. Is it 56?
Barium is actually yes, sir. 56.
It's 56 and cesium is 55. So they have the same number of electrons because this is +2 and this one is +1, right? So they have exactly the same number of electrons. This one has 54 electrons and this one 56. 2 electrons lost, so that is also 54. So when you move to the right, you got more protons, so the size of the atom or the ion decreases whenever you move to the right. You can remember this. So it's got a smaller ion as well, and it's got a greater charge as well. So your density is higher. So it's going to form a stronger ionic lattice, which is going to make it more exothermic. So the lattice energy will be for this one, it's going to be more exothermic. Is this clear?
Yes, sir. By the way, sir, for the barium sulfate and the other one, is it which one has a higher charge? Because I'm kind of confused with that one. Charge density.
Barium has the higher charge, so that's why it's got the higher charge density.
Okay, sir.
Plus, it's a smaller ion as well, right?
Yes, sir.
So barium has a +2 charge and it's a smaller ion. Actually, anyways, calculate the minimum temperature at which this reaction this entire reaction becomes feasible. So how do you figure out what is the Gibbs free energy for a feasible reaction? Negative or positive?
Negative.
Okay, for a feasible reaction, the Gibbs free energy is going to be less than 0, right? Negative. So that means Gibbs free energy is equal to delta H minus T delta S, and that should come out to be less than 0, right? So your delta H over here is given, that's 132. Temperature is the unknown. Delta S must be in kilojoules as well. Remember, the unit has to be the same. I mean, got to have similar units. So it's going to be 616 divided by 1000, I guess, and that's 0. And then you have what it's going to become. D will go to the other side, and it's going to be 132 times 1000 divided by 616, right? Is this clear?
Yes, sir.
So I'm kind of confused
Any
with
confused?
the 616 divided by 1000.
Because remember, this is in kilojoules, this is in joules, right?
Oh, okay, okay.
I mean, you always have to be careful that the units are, you have to make the units the same. You either turn everything into joules or everything into kilojoules.
Okay, sir.
So then you have barium hydroxide reacts readily with whatever this is happening. Calculate the standard Gibbs free energy for this reaction at 25. Now the first thing is for a Gibbs free energy you need two things. Delta G is equal to delta H minus T times delta S, right? So you already know the delta H over here. You also know that. I said one thing. What temperature did we get over here?
1, 3, 3,
214.3
So
degrees
that means
Celsius.
in Kelvin or centigrade.
Oh, that was 1 second, sir.
You remember this? This is in Kelvins. The equation gives you values in Kelvins, right? So you have to convert that into centigrade. If you want to go back into centigrade, you have to subtract minus 273 out of it.
Minus 58.7.
So it's minus 58.7. And let me check the answer for this one as well. That it is minus 58.7. That's minus 58.7. Anyways, is this clear that the temperature was in Kelvins, right? Is this clear?
Yes,
Yes,
sir.
sir.
I but one thing, keep this in mind that I said, keep this in mind that enthalpy is in kilojoules, entropy is in joules. So you have to make sure the unit is the same. Now this one, you know the temperature, it has to be in Kelvins for the formula to work. That's going to be 298 Kelvins, right? The enthalpy change is given. The only thing that's not given is delta S. How do you calculate delta S? Delta S is you got a formula for that, and that is that it's the entropy of the products minus the entropy of the reactants. So to apply the delta G formula, you first need delta S. So entropy of the products, what do you have? 2 NHTs. That's what is 2 NHT? That's 192 times 2. BaCl2.2H2O. That's over here. That's 203. What's the other one? 8 water molecules. That's 8 times 70 minus the reactants. What are your reactants? So you got this thing. So that's 427 and 2NH4Cl. That's 95 times 2. I guess that's about it. So what is the entropy change? Again, you have to be very careful with the calculations.
Sir, it was 530 upon 1000, which was giving me 0.53.
In this one,
Yes.
in kilojoules,
Yes, sir. I divided the previous answer by 1000.
is 0.53, right?
Yes, sir.
And then you use this to figure out delta G. What would be delta G? You're going to use that. So delta G is going to be delta H. That's 133 kilojoules minus T times that's 298 times delta S, which is 0.53 kilojoules.
Sir, I'm getting negative 24.94.
Three single figures, I guess. Okay. So negative 24.9. Okay, that's the answer. Kilojoules per mole. Is this clear? See, is this clear?
Yes, sir.
So this one transition element thing. It's he's saying that he's saying define a transition element. So what is it? It's going to form. It's stable. It's going to have stable lines with incomplete assumptions. So that's what a transition element is. Sketch the shape of a 3D z square orbital. So that's like a p orbital with a donut shaped ring in the middle. I don't know if I mean it's harder to draw this one, but that's exactly what they're looking for, right? So then, what is meant by a heterogeneous catalyst? So what is it? It's
Catalyst different from the reactants.
so this they've got a different phase or different state, right? So basically, they've got a different state from the reactants, right? Describe the mode of action of a heterogeneous catalyst in a reaction. So mode of action, it's now I don't really understand what mode means over here, but I guess he's talking about. You would have to check for the marking scheme for this one. There's an adsorption, and then there is a deadsorption process. What happens is that the catalyst, like if you have iron in the Haber process, what happens is that the catalyst weakly bonds with the reactant molecules. That's what adsorption is. And when it weakly bonds with them, the previous bonds, I mean, this is iron. So the old bonds, the triple bond electrons, they get attracted to the catalyst instead, and they break. So the old bonds, it becomes easy to break those. That's deadsorption. The old bonds, the weak bonds between catalyst and reactant molecules are going to break. So anyways, it's a 3-mark question, which is kind of exactly the same, that the adsorption of reactant to the surface of the catalyst, the bonds in the reactants, they weaken, and deadsorption. I mean, he's using the word desorbed. I mean, actually, that's not a word. It must be deadsorption or deadsorbed. So the reaction occurs and the products are deadsorbed. So you had to explain all of this in words. Is this clear? Now, he's saying manganese can be made by treatment of KMNO4 with concentrated sulfuric acid. M2O7 readily decomposes at room temperature to form manganese 4 oxide and a colorless diatomic gas. Construct equations for both the reactions described. First one, manganese 7 oxide, Mn2O7, right? What happens to it? So it can be made by, so Mn2O7 is the product, not the reactant. So Mn2O7 is being made by what? Treatment of KMNO4 with concentrated sulfuric acid. So KMNO4 reacts with concentrated sulfuric acid. And they're saying you're getting Mn2O7, right? So you're getting Mn2O7, and so that is reaction 1, and that's an incomplete reaction. They didn't tell us what the reaction is. And then they say that the Mn2O7 readily decomposes at room temperature. So your Mn2O7 readily decomposes to form manganese 4 oxide, which is manganese 4 means MnO2, because this is +4, so oxygen is -2. So the formula is going to be MnO2. And a colorless diatomic gas. What could be the colorless diatomic gas in this case? I mean, there's only
Oxygen.
one possibility, that's oxygen, right? So the second reaction, balancing the second reaction is kind of easy. It's you just add 2 over here, and you got how many oxygen? 7. So you got 4 oxygens over here, so there's going to be 3 oxygens over here. So you're going to add CO2 over here. So the second equation is kind of complete. So we're gonna come back to the first equation then. Now about the first equation, first thing is try and figure out whether it's a redox reaction. M is +7, and he's saying Mn is still +7. Like he wrote +7 over here. So this is the reaction number 1 is not redox, right? Is that clear?
Yes, sir.
So that kind of shows us that the oxidation state is not changing of any substance. So what do you think are the other substances? You got 2 Mns, right? So there's going to be 2 Mns over here as well, right? So what do you think is the other thing that's produced along with it? Yeah, you got K, you got SO4, so I guess my hunch is it's going to be K2SO4, right? Is that clear?
Yes, sir.
What happened to the H then? You got 4 oxygens. There's 2H. There's 1 oxygen left, right? What happened to the? Yeah, you got 12 oxygens, right? Right now you've got 11. So there's a water molecule getting produced as well. Is this clear?
Yes, sir.
So that's it, I guess. Now, aqueous manganese 2 ions show similar chemical properties to aqueous copper 2 ions, which react separately with NaOH and with concentrated HCl. So write the equation. Now, remember, for transition metals, copper 2 ions, they're saying they've got similar chemical properties to manganese 2 ions. So we know equations for copper 2 ions. We're going to use the same equations for Mn ions. So write the type of reaction with NaOH. So what happens with M? Now imagine copper. So what happens is that when you add OH ions to it, what happens is that MnOH twice is formed. The ligands, they get replaced by OH ions, and the 2 water molecules, they get knocked out, and you got a solid precipitate. So precipitation happens. You can remember in transition metals we did this reaction for copper. Over here he's asking us for Mn, and the same with and the same one for Cl lines as well. So the water molecules, they get replaced by Cl lines, and 6 water molecules, they get knocked out. This one is ligand exchange. Is this clear?
Yes, sir.
And let me just check the double arrows. I mean, should have been a reversible sign over here. But anyways, precipitation and ligand exchange, I guess I think they just didn't have that. And also remember, MnOH2, H2O4, it's the same as MnOH2. Both are acceptable. Now we've got this reaction. He thinks suggests the formula of the manganese species formed when Mn2 plus reacts with Cl2 state the type of reaction. So we've got a reaction of Mn2 plus with Cl2, right? What I'm going to do is I'm going to write down all reactions involving Mn2 plus. Wherever I see Mn2 plus, I'm going to write that reaction, right? And Cl2, where is Cl2? You got 2 reactions for Cl2, right? So we've got 2 reactions for Cl2, we've got 2 reactions for Mn2 plus. Is that clear?
Yes, sir.
So ignore the last one for now. Now, who's got the highest potential out of all of these reactions?
The fourth one, sir. Fifth one, I mean, 1.67.
We're ignoring that at the moment because the first thing is we've got Mn2 plus and we've got Cl2. The fifth one does not have Mn2 plus. or Cl2. It doesn't have both.
Okay, so then it will be chlorine, so 1.64, reaction 3.
But you're going to reject it because the higher potential is the one, because we're looking for the higher potential, right? Higher potential is the one that gains electrons. So we wanted chlorine to gain electrons. So over here, we've got HOCl that's gaining electrons. Is that clear?
Yes, sir.
So we're going to ignore that. Ignore that. Now figure out, is that clear why we rejected it, right? Is this clear?
Not very, sir. I'm confused.
It's higher potential is the one that gains electrons, right?
Yes, sir.
Remember, they were to solve a question like this, you had a couple of steps. The first thing was you're only going to select equations that have Mn2 plus or where something is happening to Mn2 plus or Cl2, right? So these are the reactions that involved Mn2 plus and Cl2. So I selected those, right? Is that clear? And I rejected the
Yes,
last
sir.
one.
Okay, so it's going to be between first and second, and we can choose Cl2, which is 1.36. But it's going to gain
First,
electron, but
the first and second. Need, I guess
yes,
it's let's figure out who's the higher potential, right? Right now it's 1.64, right?
yes, sir.
But it's the wrong one, right? Because that means it's going to gain electrons. That means HOCl is the one that's going to gain electrons. We don't have HOCl as a reactant. Is that clear?
Yes, sir.
So which is why I'm rejecting it, because although it is the higher potential, I mean it's obviously the higher potential, but it's something else that's gaining electrons. So you can't select that. If you reject that, who's the higher potential? It's this one, right? We're gonna cut that out. It's 1.36, and that perfectly matches our potential, right? Is this clear?
Yes.
So that that perfectly matches our potential, which is I mean, and our reactants. It's Cl2 that's gaining electrons. So I figured out who's the higher potential. That's the one that's going to gain electrons. Now I'm going to figure out who's going to lose electrons. Who loses electrons is the one that has the lowest potential, right? So Asina, which one is the lowest at the moment?
At the moment is first one, negative 1.18.
So that's going to lose electrons, but I'm not going to select that. Why? Because it's Mn that's losing electrons. I don't have Mn. I've got Mn2 plus. I don't have Mn. Is that clear?
Yes, sir. It's going to be 1.23.
It's going to be 1.23. I have it, so it's Mn2 plus. So that's fine. That's so. So the higher I figured out is, I mean, I figured out this equation, and I figured out this equation. So the formula of my manganese species that's formed, that's MnO2, and the type of reaction, I guess that's a redox reaction. ठीक है, that is a redox reaction. That's a redox reaction, and that is what's going to happen. Is this clear?
Yes, sir.
Okay, so coming back to this, remember, you're only going to select equations that involve Mn2 plus and Cl2. And then the other point is that the higher one gains electrons, but it has to be one of these two that's gaining electrons. If it's somebody else gaining electrons, you're going to reject that. The higher came out to be 1.64, but it was HOCl that was gaining electrons. So there is no HOCl here. So you rejected that. The higher came out to be 1.36. It was Cl2 that was gaining electrons. So that is fine. Cl2 gaining electrons. You figured out the lowest that loses electrons, but it has to be one of these that loses electrons. So lowest came out to be minus 1.18, but you rejected it because it's Mn losing electrons. You don't have Mn over here. And finally, you came out with 1.2. So you do have Mn2 plus. So is this clear? It was just a 1 mark question, by the way. Now, the next one is about rate of reaction. You've got now the next one is about rate of reaction. So they plotted the concentration of one of your reactants. the halogenoalkane. I mean, there are two reactants, right? So one of the reactant concentration with respect to time is plotted. So what can you figure out using the half-life method?
Reactor used up.
What does the half-life tell you?
Half, the theory was like how a reactant is half of what it was in the starting.
I mean, there were two. There was order 0.
It's order 0, order 1, and order 2.
Yeah, order 0 was that you're going to get a straight line. Why? Because if the concentration decreases, if the reactant concentration decreases, the speed does not change. It just decreases with a constant speed. Is that clear?
Yes, sir.
Order 1 was that the half-life will be constant. So this one over here is actually order 1. That whenever the concentration decreases, it takes a longer time for it to, the reaction slows down proportionally. I mean, the reaction concentration decreases, it takes a longer time. Reaction concentration decreases, it takes a longer time. So it just becomes an asymptote. It just continues endlessly. Okay, so and the half-life is constant. You can check the half-life. That's the first one. That's your second one. That's your. They all look exactly the same. So this is, I mean, the first one. That's order 1. Is this clear?
Yes, sir.
So then he's saying, show your working, figure out the rate of reaction at 40 seconds. What you're going to do at 40 seconds is, I think 40 seconds, you're going to put a ruler, a scale at 40. So I guess this is, so you're going to make a gradient. And that's going to be your gradient at 40 seconds. Is this clear? And you're going to measure the rate or the gradient of this graph. Is this clear?
Yes, sir.
So I guess it's going to be a rough estimate because this is like, I mean, what's the y change in y? That's 0.0150 moles per dm cube. What is the change? What is the change in x? That's the time. That's I guess that's 90. What's the midway of or 88? Let's say 88 seconds, right? So what do we get for this?
So is it 1.7 times 10 to the power of negative 4.
1 point.
1.7 times 10 to the power of negative 4.
Mole per dm cube per second. We'll just have a double check this one. I mean, we're exactly getting the same answer, by the way, even with a rough. So calculation of gradient. Evidence of tangent drawn at t0 to 40 seconds, and that's we got exactly the same value, by the way, 1.7. Yeah, so we got very lucky, but and minimum 2 signal figures. Anyways, there must have been a range over here. So the next thing is use the graph to show that the overall reaction is first order. We did that. We already did that. It's order 1. Is that clear? What happened in order 2? In order 2, the reaction would slow down too much, right? So every half-life is double the previous half-life. Is that clear? It takes a much longer time for the reaction to finish. Is this clear?
Yes, sir. But sir, like if you had to do a rough sketch of the second reaction, order 2 reaction, what would it look like?
Like if you were to sketch it,
Yeah, like just a rough sketch.
the rough sketch would be that let's say I mean, that's your half-life, right? I mean, this point. This point will be double the previous one, right? So it's going to be somewhere over here. So every half-life is going to be double the previous half-life. I mean, it's going to look like this. Like, let me just show you. So graph half-life, second order. So for a second order reaction, that's like constant half-life. 1 second. Yep, this one. So if you were to look carefully, 1 second, open image. So for this diagram, if you look carefully, that is first order. The half-life is always like the time taken for the concentrate. It's always constant, right? And that's your every time it's doubling. Like first time it took up to this red mark. That's the first half-life. Second time the concentration decreases by half. It takes double the time. Third time it takes a much longer time. Is this clear?
Yes, sir.
So the time doubles, and that's what you're going to measure. You're going to measure the half-life. Like what is the time? You started off at 0.2, 0.1. That's your first half-life. From 0.1, you're going to go to the second. That's the second half-life. So it takes this much time. Then you're going to go to 0.025. That's the third half-life. Every time it's the same time that's required. So that's first order. Anyways, in a different reaction, which is also first order, 75% of the reactant is consumed in 320 seconds. So calculate the rate constant, state the units for K, and so he's saying 75% of the reactant is consumed in 320 seconds. Calculate the rate constant. So there's a different reaction, which is so it's a totally different reaction, and which is also a first order reaction. And 75% of the reactant is consumed in the first 320 seconds. How many half-lives is that? You started off at 100%, right? And it's a first order reaction. That means the half-life remains constant. So there's a certain amount of time that's required, and the concentration is going to decrease by half. It's going to become 50%, right? So that's the first half-life. Then the second half-life, the concentration is going to decrease by half again. It's going to become 25%. That's your second half-life. Is that clear?
Yes, sir.
Now, in a first order reaction, the half-life is constant, right? So the half-life is constant. That means the first half-life value and the second half-life value is the same. Like if it takes 10 seconds for the concentration to decrease by 50%, it's going to take another 10% for the concentration to decrease by 50% again, right? Is this clear?
Yes, sir.
And the graph would look like it's like if it takes 26 seconds for the concentration to decrease by half, it's going to take another 26 seconds. Like if it's going to become 55 or whatever, it's going to decrease by half again, right? So if the whole thing is 320 seconds, because that's a decrease of 75%. So if the whole thing is what, 320 seconds, so that means it took 180 seconds for the concentration to decrease by the first half, and 180 seconds for the concentration to decrease by another half. Is this clear?
So where did we get the 180 from?
Can you speak louder? I can't hear you.
Where did we get the 180 seconds from? Like
Wait, why do
the
we?
recording? Oh, okay, got it, sir. No worries. Got it, sir.
Okay, so we got the half-life, right? Your T half-life is what? It's 180 seconds, right? Is that clear?
Yes, sir.
Actually, now there's a formula for finding K, which is 0.693 divided by the half-life. Why is it taking? Actually, sorry, it's not 180, it's actually 160. Like 320 divided by 2 is not 180, it's actually 180, 160 seconds. Actually, now there's a formula for finding K, which is 0.693 divided by T half. So we know it's on 160 seconds. So it's going to be 0.693 divided by 160. So we figured out the half-life, that's 160 seconds. And we got the constant, the rate constant K as well. Is this clear?
Yes, sir.
And define the term standard electrode. Actually, remember this thing. This is the rate constant for the equation 0.693. This is probably the only question where they actually asked for finding the rate constant using this formula. It's been there, but they never actually asked for this ever. But remember this: if you figure out the half-life, the rate constant K will be 0.693 divided by the half-life for the first order reaction. So define the term standard electrode potential. It's the potential calculated between potential difference that's calculated between a standard electrode and a standard hydrogen electrode. They're asking for the function of the salt bridge. It's for completing the circuit and to stabilize the ions or kind of maintain the concentration of the ions in solution. TK, what's the completing the circuit, maintain the charge balance, or maintain the concentration of the ions? So TK, let's continue with this tomorrow then, right?
Okay, sir.
Okay, sir.
Okay,
You can try going through these questions and see if you have any problems. You can make sure you bring your problems now.
okay, sir.
Okay
Okay,
then.
bye, sir. Good night.
Thank you, sir. Lafis.